Hi everyone. This video is going to be about partial derivatives, section 14.3, and I'll say ahead of time that if you already know how to do things like product rule and you really understand the chain rule and things like that, the computation for this is not that hard. So we're just going to be doing pretty normal derivatives here with one extra little special characteristic in here. What I will say is that this concept is something that we use a lot. So if you can picture kind of those problems where we used vectors to figure out maybe these are two vectors on the plane and then cross product to find the normal vector of that plane. We're going to be using partial derivatives in that same way. So kind of understanding what they look like conceptually and visually is going to be just as important as being able to solve for them. So we'll talk about kind of how to do them first and then what they are a little bit later. So let's say that I have a function of two variables, f of x and y, and that one's going to be equal to x squared times sine of y. If I want to take the derivative of this function, if we only had one input variable, there'd only be one option, right? We would just want to take the derivative with respect to x or with respect to y, but here we've got two options. So instead of writing d dx, we write what's called a del. So just like a curvy d here, del f del x. And I'll just show you what we're going to do first. So we're going to treat x like a variable, and we're going to treat y like a constant. So I'll write that down. We're going to treat x like a variable, and y like a constant. And you can kind of see here, so I like to almost just kind of picture, right? I just replace it with 7 in my mind, right? So I can just kind of have an intuitive feel for it. So this is sine of 7. 7 is going to be, sine of 7 is going to be a constant. So some constant times x squared. If you take that derivative like, sine of 7 times x squared, that's just going to be sine of 7 times 2x. The other option is going to be the complement to that, right? So df dy is going to be equal to let's see, x squared. So x squared is going to be that constant, and then the derivative of sine of y is going to be cosine of y. Here we're going to treat y like a constant, and x like a variable. And this is a pretty straightforward example. Kind of some of the subtle points that I want to make here are that it's going to seem silly when I do this. So df dx, I want you to kind of think about this as being having two meanings, right? So the first meaning is the change in f with respect to x. So how does f change as x changes? And you can also think about this as the partial derivative with respect to x of f. So there's kind of two actions that we can do to describe the same thing. One, we can talk about how is f changing with respect to x, and taking the partial derivative, so kind of applying a partial derivative to f. A third way that we can even think about this is, remember, commonly we can write f of xy is equal to z. So we've got some function, and we kind of set that equal to z when we want to graph it. Right, so we have, there's our surface, right? And we plot that on the z-axis. So we can also write del z del x, as long as we make that kind of distinction, right? If f of x, y, right, if we just set that to some variable z. So yeah, those are the ways that we want to think about this. You're either performing an action, you're taking the partial derivative with respect to x, or you're seeing how, this is really the way we want to think about it, right? Like, how is z changing as we move along the x direction? Let's look at a couple more just to get some practice. So let's say that g of x and y is equal to e to the x sine of y plus e to the y cosine of x. So the partial derivative with respect to x, we're going to treat x like a variable, y like a constant. So x is the variable, y is the constant. So sine of 7 times e to the x, so that's like some constant times e to the x, is just going to be, well, the derivative of that is e to the x times that same constant. This next one, we're going to treat x like a variable, y like a constant. So e to the y is a constant, but x is a variable. So some constant times cosine of x is going to be, it's going to be negative sine of x, and then we need that same variable around. Del g del y, very similar, right? We just kind of switch which one we are going to be changing around. The third one to think about, so this is kind of going to be the first one where we have to think about this in terms of calculus concepts. So this is e to the x times y squared. And if we think about taking the partial derivative with respect to x, we're going to treat x like a variable, and y like a constant. So we have e to the some constant times x. So if you think about e to the 7x, if we want to take the derivative with respect to that, then we're going to get something like 7e to the 7x, right? Because we have, we just basically take the derivative of whatever we have up here and throw it out in front. So that'll get us most of the way there, right? So we can write this out. So that's going to be what? The derivative of this, so it's going to be y squared times e to the xy squared, right? That constant just coming out in front here. I'd like you to think about it in this way, though. So we have that chain rule, right? So what we're going to do is set u equal to this xy squared up top here. And then we're going to use the fact that this is equivalent, right? That those u's in some sense sort of cancel out and give us del x, del h, del x. And these are pretty easy to figure out, right? So del u del x, that's just going to be the derivative, the partial derivative of this with respect to x. There's our y squared. This is del h del u. So this is the partial derivative of u with respect to x of h. So e to the u, right, times del u del x, which we decided was y squared. We can just kind of picture this as the partial derivative of some variable, e to that same variable. That's just going to be e to the xy squared times y squared. So I think this method, just trying to kind of play the scenario out in your head where you treat y like a constant, is fine most of the time. It can get you in trouble though, right? Like it's much easier to make mistakes, and this is much more, this is easier to grade, right? Certainly more partial credit is going to be rewarded for attempting it this way because I can see where the mistake happened. If you just write the wrong answer here, I can't do much about that, right? Yeah, so let's do the y one as well. So u in this case is going to be xy squared, so we can think about what del u del y is going to be equal to. Del u del y is going to be x times 2y, or just 2xy, probably an easier way to say that. This is the partial derivative of h with respect to u. That's going to be the same thing, right? We already figured that piece out, e to the xy squared. I don't know if this will be helpful for you. I always think of this as kind of being, this is like the naive part of it, right? Like you wish that this was all you had to do, right? If you're taking the derivative of this with respect to x, you just kind of say, well, e to the x is blah, blah, blah. So I'll just kind of take, I'll just kind of pretend this is there and then make this correction factor in here. Maybe that's a helpful way to think about it. Look at a few more. So let's say I've got some function m of x and y. So we know what this looks like when it's x to the 7th, right? So let's do that x1 first, right? Del m del x. We treat x like a variable, y like a constant. Right, x to the 7, 7 minus 1, right? So this is just going to be y times x to the y minus 1. This is probably the most common derivative that people forget how to do. Right, 7 to the x, so that's going to be natural log of something times 7x. So it is that base, right? Whatever the base is, that's going to be what you multiply it by. So in this case, x is the base. We treat it like a constant, so 7 to the y. That's going to be ln of, and technically it's absolute value of x. And then we're going to multiply that by xy. One more, and then we'll talk about a different topic. This one is going to involve the product rule. Um, Thinking about this one is going to be a little bit tricky. I think I'll just do, uh, well, let's do y first, right? So del and del y is really easy, right? That one's just some constant times, or a variable times some constant, right? Sine of x times x. So we're just going to get whatever that constant is. 7 times x, derivative of that is just 7. Del n del x is going to be a little bit more complicated. So now we have, right, we're taking the partial derivative with respect to x of sine of x times y. And because this is a constant, so we know that, like, if you want to take the derivative, right, of 7x squared, we can simplify this by kind of taking all the things that all the constants out in front here. So we can go ahead and do that here, right? Like, since we're treating y like a constant, we can just bring it out in front here. So that's going to be y times the partial derivative of sine of x times x. That's going to be y times, and then now we just have a product rule to do, right? Partial derivative with respect to x of sine of x times x. That's going to be, let's see, sine of x times 1 plus derivative of this one, cosine of x times x. Product rule, chain rule, just things you want to think about, right? There is one other category of these types of things that you may not have seen before, and those are implicit. So these are the implicit partial derivatives, and I'm going to draw an analogy to what we already know, excuse me, from calculus. So when I say something like y equals 3x squared, and I want to find y prime, or I want to find dy dx, really what I'm doing is kind of taking the derivative with respect to x of both sides, all right? And on this side, I'm going to get, right, we know that just dy dx, that's fine. And then here, we're obviously going to get 6x. But the idea is that we're taking the derivative of both sides. Like, you can always do that. If two things are equal to each other, you can always just take the derivatives of both sides, and that equality is still going to hold. It's just like, you know, adding 7 to both sides or dividing by 8. But that's kind of the most common scenario where you have like y equals something. But you could also have it in an implicit form. So I could have something like 3y to the 4th plus x to the 7th equals 5x. And suppose I wanted to find dy dx. The way that I can go about doing that is this same process, right? Just taking the partial derivative, or not the partial, the derivative of both sides. We'll end up taking the partial later. So I'm just going to go ahead and do that. right? Take the partial derivative of both sides. This side is going to be equal to 5, right? Taking the derivative over here, this piece will be 7x to the 6th. And this piece is going to be 12y to the 3rd. But the thing that we have to keep in mind here is that y is a function of x, right? So it's not just, if we're going to take this derivative with respect to x, we need to think about how this is going to change. So a couple ways to think about this, one of which is we can consider this whole thing f. So we're kind of taking right, we're kind of treating this, even though we're taking the derivative with respect to x, we're kind of treating y like the variable, so df dy, and then we have to multiply it by dy dx. The other way to think about it is we need chain rule because y is a function of x. So what that means is it's not just 12y to the 3rd, it's going to be 12y to the 3rd times dy dx. So we need that dy dx term. Right now, our goal is to find dy dx, so we can take this in its current form and we can just write that out. So that's solve for this variable here. So it's going to look like 5 minus 7x to the 6th divided by 12y to the 3rd. That's equal to our dy dx. So let's see what that looks like in multivariable calculus, right? This is kind of this process that we're doing is we're starting with the implicit. This would be explicit. We're explicitly told what y is. We're just finding the derivative of it. Here we've got some implicit relationship. Y is kind of hanging out in here. So here's what that's going to look like in multivariable. Let's say I have a function, or not a function, right? Just this equation. So that's an x squared, that's a y squared. And our goal is going to be to find two things. We're going to find del z del x and del z del y. And we'll do this one first. But just like in the last one, the insight that made it so that we use the correct derivative was that y is a function of x. Here, remember that really common equation that we write where z is a function of x and y? We're going to do that same thing here. So we want to keep in mind that z is a function of x and y. So z is a function of x, z is a function of y, and we'll treat it as such. So one way to do this would be to solve for z, right? But I want to try a slightly different method. If you solve for z and then take the partial with respect to x, partial with respect to y, you'll get a square root, and then you'll get this kind of really nasty equation that you have to do in here. So we'll just say this, like z is equal to plus or minus, right, x squared plus y squared divided by x to the third. If you want to kind of try to take this derivative and then look at the plus or minus version of that, by all means go ahead and do it, but we'll say this is difficult to say the least. Okay. So instead, let's try we can take the partial derivative with respect to y of both sides. So let's see what that looks like. Delta y of x to the third z squared is equal to delta y of x squared plus y squared. Let's do the right-hand side first because that's the easy one. So this is a constant that gets reduced down to nothing, or 0 rather, and this will just be 2y. This one, however, we've got this thing, which we're going to treat like a constant. So it's some constant. And then we don't treat z like a variable that we're differentiating with respect to, and we don't treat it like a constant. It's this third item where it's a function of x and y. So if we're going to take this partial derivative of something, we treat this not just like a variable, but like a function. So it's going to be, we can even say, well, this is we can treat this like a constant. So we can just pull that out in front. This is going to be x to the third, and then this is going to be 2z, like you might expect, but we're also going to have a del z del y in there. Last piece is going to be solving for this del z del y, and that's just algebra. So that's going to be, looks like 2y divided by x to the third 2z. The fact that we have a z in here still, that's just the way it's going to have to be, right? So no getting around that. When we try to find the partial derivative with respect to x of both sides, that's going to look like this. Oops. Del x of x squared plus y squared. Again, right-hand side is going to be very easy. That's just going to be 2x. Here, we want to think about the fact that, again, z is a function of x and y. So if you want to take the partial derivative of x to the third multiplied by some function squared, you're doing the same thing that you would be doing here, right? Right. This is some function of x, and this is also some function of x. So if you want to take these two derivatives, or if you want to take the derivative of this piece here, right, it needs to be this, right? And these are derivatives with respect to x. Whoops. F prime times g plus g prime times f. So we do need the product rule there. let's go ahead and apply that. So this is going to be x to the third times the derivative of this thing with respect to x. So that's going to be 2z, but we also need del z del x in there. And then this one, z squared times the derivative with respect to x of x to the third. So that's going to be z squared 3x squared. From here we can solve for del z del x. All right, just using algebra, we can find that. I'll get a 10% battery, I might as well do it. Okay, there we go. So that's going to be it for partial derivatives in terms of actually computing them. There is one other slide that I want to make, which is kind of describing what's going on with them. So we can make an analogy with what we know about derivatives from calculus. In R2, right, you've got some function f of x, and let's say at this particular point, right, the derivative at that point, we can say the slope of tangent line is equal to dy dx, right? It's a measure of how y is changing as we move one unit in the x direction. Right, so as you move forward in one x unit, how is y changing? In R3, very similar concept. Except here, now we've got, instead of a curve, we have a surface. And I'll make that same point here, right? So let's say I have got some point, right, some x and y point, and I evaluate the function there. It's still going to be the slope of a tangent line, but we've got multiple tangent lines to look at. So one thing we could think about is if we've got del z del x, so this is kind of answering the question, how is z changing as we move in the positive x direction? Right, here the same thing, the same exact thing that's happening here, right? Like as we move in the positive x direction, how is y changing? So you can picture as we move in this direction, maybe in this surface that I drew, it doesn't seem like z is changing at all, right? Maybe it just stays right at 7. Del z del y, that's going to be how z is changing as we move in the positive y direction. And I've kind of drawn a little wiggle here, so as we move along that y-axis, right, if we take a step in the y direction, how is that surface changing, right? Is that surface going up or down? So you can picture, right, like this dome. If I pick this point here and I move in the positive y direction, z is decreasing, right? So for this point, del z del y, would be negative, because as we move in the positive y direction, z goes down. I'm going to attempt to kind of connect why we set these variables equal to constants. If you're taking the partial derivative with respect to x, for example, then you treat y like a constant. So I kind of want to give you an intuitive sense of what's going on there. What I'm going to do is take this drawing that I've made here, and I'm going to kind of look down onto it. So I'm going to take a top view of this. So that's going to look like, and I'll kind of rotate it so that we have a nice y and x axis. So in this case, z would be coming out of the page. But here's our surface, right? Right, here's that same surface, the y and x. If I want to take the, let's say at this point, if I want to find the partial derivative with respect to x, I want to see how this surface is changing as I move along the x direction. All right, so I take one step in the x direction. How is the surface going to change? And if you think about all the different points that you could make and find that partial derivative with respect to x, the common thread between all of them is that I'm treating y like a constant, right? Like, so if I'm interested in taking the derivative along the x direction, the restriction that I'm making here is that y is, let's say, equal to 1, right? So if you treat y like a constant, that kind of helps you move along the x direction, right? You're placing a restriction on yourself. Same thing if I wanted to take this point here and find the partial derivative with respect to y, I'm treating x like a constant. I'm saying, okay, if x is whatever constant I'm at right here, and I move one step in the positive y direction, how is my surface changing? This is going to be useful. Like I said, this kind of builds the foundation for what we do later in the class, because as we'll see, you can take the partial derivative with respect to x. You can take the partial derivative with respect to y. There's also some third option where you say, hey, off in this direction, how is z changing? So we'll define that with vectors, and that'll be called directional derivatives. But for now, I just want you to kind of recognize that we're doing the same thing that we did in Calculus 1, right? Change in y with respect to x. Now we're just treating x and y like inputs, and z is going to be our curve. All right, so that's it.